Everybody doing okay? Right. It's probably starting to set in a little bit, like summer's over, starting to feel it a little bit more, right? Homework's happening. You got an exam. Don't you have an exam in 205 coming up? Or quiz? What's it today? Oh, not 205, but a different class. Yeah, you just scared some people in here. You're like, oh shit, we have an exam today? So anyways, it's coming, right? Just let it wash over you. Just let it happen. I don't know. One thing I remember from engineering school is that it is a lot more intensive than some of those other branches. Some of you that maybe know some business majors, you're like, what the hell, right? Like they're never doing homework and just partying out. Yeah, but you've got a goal in mind. You have a job waiting for you at the end. It's great. So. Oh, I've got a joke about what's it? Oh, because like right as let me see if I got it. Okay, so you guys are engineers, right? You call yourselves engineers, but you actually haven't graduated from engineering school yet, right? So you don't hear doctors, like pre-med students going around calling themselves doctors yet, right? And you don't hear art students going around calling themselves unemployed. There you go. There you go. That's my joke for the day. Okay, so just like we do every time, it's a quick little review, kind of get oriented where we're at. Particle kinematics. We just covered this new coordinate system called polar coordinates. Well, it's at least new to us in this class right now. You have position defined going from the origin up to a location, and then ER points in the direction of R. And then E theta is in the direction of increasing theta perpendicular to R. It's different than normal tangent. We went through the derivation of that, and we ended up with this guy right here for the definition of acceleration. So just when you're in this coordinate system, you just know when I'm going to write down velocities, I use this equation, r dot in the ER plus r omega in the E theta. That's the equation you use for velocity. And then for acceleration, this is the equation I use for acceleration. This thing has a bunch of different components to it. The radial, we use as an example this merry-go-round. The radial acceleration is if I'm on the merry-go-round and I'm sprinting to the outside, it's how fast I am accelerating towards the outside. R omega squared is the centripetal acceleration. I have to be accelerating back towards the middle. If I do not accelerate back towards the middle, I go flying off, right? R alpha is associated with omega increasing. So that's the motorcycle on the side, the guy gunning it, and it's accelerating. You would feel a push, like if you're standing on it, you'd feel the merry-go-round speeding up. That's this R alpha term. And then there's also this Coriolis. Every time I take a step out, I have to increase my tangential velocity or my E theta velocity. Every time I take a step out, I have to go faster that direction, faster that direction, faster that. So you feel this kind of push to the side. That's the Coriolis, right? We did a couple of very simple examples with that. You can convert back and forth between between polar coordinates and Cartesian coordinates. We're going to do an example today where we're going to have to do that, right? Because the one thing that's weird about normal tangent and polar coordinates is they help us define forces and things that we feel. Like I step out and I feel the push from the side, right? It helps me describe that, but it doesn't help me identify where I'm actually at, right? Because that coordinate is actually moving with me. So to define where I'm actually at, like position-wise, this is a little bit more confusing. That's why we have to go back to another another coordinate system, in this case Cartesian coordinates, in order to make like sense of that. It'll come up in an example today. So we did a couple of examples associated with that, and then we introduced this idea of relative velocity. It basically is just vector math. If I want to go to A, I can either go right to A, or I could go to B and then over to A. And both of those work, right? RB plus RA as seen from B is the same as RA, okay? It's just the way vector math works. Same thing with velocity, right? I go velocity of A is equal to velocity of B plus the velocity of A as seen from B. Take the derivative of that, I get acceleration. Acceleration of A is equal to acceleration of B plus acceleration of A as seen from B, right? And when I see this slash, right, I always say as seen from. That's or relative to, you could say A relative to B. I like saying as seen from, so I picture myself at B looking at A. Okay, and then we did like this real quick example. and then just said, oh, look, the frisbee is equal to the velocity of the plane plus the velocity of the frisbee as seen from the plane, which makes sense, right? Just logically, this argument makes sense. I want to see the total speed of that frisbee relative to the Earth. I figure out how fast the plane is going, and then how fast is the frisbee traveling relative to the plane. It makes logically, it just makes total sense to do that. Pointed out a wrong answer from your homework. Okay, so this is an example. So we have an airplane pointed due north. Airplane is pointed due north. It has an airspeed of 560 miles per hour, and the wind is traveling at 60 miles per hour at 30 degrees as shown. We actually have, it's not shown, so let's draw it. Let's go like this. That is the X, Y direction. So my plane, my aeroplane, it's a stick figure airplane. Okay, so it's pointed due north, and it's traveling at and it says an airspeed of 560 miles per hour. That just means that relative to the air, it is traveling, it's pointed north, and it's traveling 560 miles per hour. How that's recorded is there's like a little, somebody who was in the Air Force told me this, that there's a little like instrument on the outside of the airplane that measures how quick the air is going by it, which kind of makes sense. And so if you have that little instrument on there, and you're traveling, what you're feeling is, or what you're measuring is how fast you're going relative to the air, not relative to the ground. Nowadays, GPS and all that other stuff that would be able to tell you exactly your speed, and it would take into consideration the fact that the wind is moving, or the air is moving as well. But back in the day, they didn't have that. There's a little instrument that told you how fast you were moving relative to the air. Okay, so that's what it is. And then what we're asked to find is the ground speed and course. So ground speed is just how fast you're going, and course is what your direction, like which direction are you actually moving. Okay. All right, so let's do this one. So this one, we're just going to use that relative motion stuff and say, well, the velocity of the plane is equal to the velocity of the wind plus the velocity of the plane as seen from the wind. And logically, this stuff is pretty easy. Now, this is the same as VA is equal to VB plus VA as seen from B. That's all it is. I put in the variables there. Okay, so V wind, all right, so V plane is seen from wind. Right. That is 560 in the J. Right, it's pointed due north. Right, it's directed pointed straight up north. But as it's moving north, I mean, just to kind of take a step back, the thing's pointing straight north, but the air is moving like that, so it's actually traveling like this to kind of to the right. Right, just moving to the right. Okay, and then we're trying to figure out how much is it moving to the right. It's going 560, but it's got this little side push to it as well. Okay. The V wind, all right, just leave this thing in vector form. It is 60 at that angle of 30 degrees. We have to put it in vector form. So this would be cosine 30 in the I plus sine 30 in the J. Right, so the magnet has a magnitude of 60, but it's at that angle there. So we just look at this. I mean, I'm just breaking it down into the I and J components. Right. Those two green arrows there. Putting it in that. And so then the velocity of the plane, just add the two together. Right, plane is equal to 60 times cosine 30 in the I plus sine 30 in the J plus 560 in the J. Right? And then what you do, I just plug that sucker in my calculator, and I get 51.96 in the I plus 590 in the J. That's almost the answer. If I want the total airspeed, so that's what it's doing, right? It's doing so really it's only going 560 relative to the air, but it is going 590 in the y. So it's the actual speed relative to the ground is 590 in the y, but then it also has a little bit of an x component, 51.96 to the right there. And so the airspeed would be the magnitude of that. Square root of the sum of the squares, so it's actually traveling at 592.3 miles per hour. That's its airspeed. Or sorry, ground speed. And then this is just, I put it in perspective, this is 590. And then it has a component to the side of 51.96. And so what I'm after for that course is I'm after that angle right there. That theta is going to be equal to the inverse tangent of 51.96 over 590. And so that ends up being just about 5 degrees. So the ground speed is 592.3 miles per hour, and then it's just off north by 5 degrees. That was a really simple example. Any questions about that? Okay, let's do this next one. This one's a little more interesting. This one combines polar coordinates and relative velocities and relative accelerations. Okay, so this is, I may have made this one up. Okay, so you have this car right here. It's traveling around in a circular path, right? And you have car B, and it's traveling around in a circular path as well. Right? So two different cars traveling around circular paths. And the problem, so velocity of A is 36 feet per second. Velocity of B is 45 feet per second. Okay, and RA, the radius of A is 1250, and the radius of B is 1200. And so what we're asked to find is the magnitude of the velocity of B as seen from A, and the magnitude of the acceleration of B as seen from A. Okay, and so let's get started, right? So it's basically as if I'm at, was it B as seen from A? So basically if I'm at B looking at A, how fast is A going relative to me, okay? And same thing with acceleration. If I'm at B and I'm looking at A, how fast is, or what's the acceleration of A as seen from B? What does it look like when I'm at B looking over at it, okay? This comes up a lot when we do rigid body stuff, so we kind of introduce it here. All right, so if I'm at velocity, let's kind of go back to this definition of the relative velocity. So the relative velocity of B is equal to the velocity of A plus the velocity of B as seen from A. Right, that was kind of our definition of relative velocity stuff, but what I'm after is the velocity of B as seen from A. So you just do algebraically, just solve for VB as seen from A. So that makes it VB as seen from A is equal to VB minus VA. Right. Same thing can be done for accelerations. Acceleration of B is seen from A is equal to acceleration of B minus acceleration of A. Kind of laying out, that's what we want to do. And we're going to start it off on what we're trying to do. Okay, that's what we're after. So to do that, I have to figure out what VB is, and I have to figure out what VA is, then I have to figure out what AB is and what AA is. So I just have to do that right now. So let's just go through and define that. This thing is traveling in a circle, right? So when things are traveling in a circle, it's most easily done using either polar coordinates or normal tangent coordinates. You could choose either one of those things, right? They give you the exact same answer. I like polar coordinates better, so I'm going to use polar coordinates. So I'm going to figure out the velocity of A and the velocity of B in polar coordinates, and acceleration of B and acceleration of A in polar coordinates. Okay. And then we'll see, then we'll have to do a little something else. All right, so let's do car A. Again, we're going to do polar. say VA is equal to R omega in the E theta, or it's equal to just the velocity of A in the E theta direction. I kind of went up above, and you can kind of look at a circle in polar coordinates. You know, it's the velocity of A in the E theta direction. We wrote it, it can be written as R omega in the E theta direction, or if you are actually given the velocity in A, it's just going to be the velocity of A in the E theta direction. So they actually give us the velocity of A, and that's 36. So this is 36 in the E theta direction, and the units are feet per second. So that's the velocity of A. Then we do the velocity of B. The acceleration A. I'm dealing with car A right now. So acceleration A is going to be R alpha in the E theta direction minus VA squared over RA in the ER direction. Okay. R alpha is 0, right? Because it's traveling at a constant velocity. If it's traveling at a constant velocity, then omega is constant. If omega is constant, then alpha is 0. Okay, so R alpha component of that acceleration is 0, and so you're just left with the centripetal acceleration, which is VA squared over VA squared over RA. So this ends up being negative 36 squared over 1250. I don't actually calculate that right now, and that's in the ER direction. Okay, so that's the acceleration of A. Let's do car B now. So we have acceleration of A and velocity of A, so let's do car B. Again, in polar. Velocity of B is equal to VB in the E theta direction. VB is 45 in the E theta direction. Okay. And then acceleration of B is equal to R alpha in the E theta minus VB squared over RB in the ER direction. Again, at R alpha is 0 because it's traveling at constant velocity. And so this is negative 45 squared over 1200. Okay. So like, and so we know what this velocity and acceleration are. Okay. Now, I think it's because that one's closer. I always go that way. Because this is when I gotta walk all the way over here. So much further. Okay. So this is great, right? So I look up there, I say the velocity of B is c from A, it's just VB minus VA. Acceleration of B is AB minus AA. So I can just take 36 in the E theta minus 45 in the E theta minus 36 in the E theta. Can I do that? Can't do that. Why can't I do that? Because there are two different E thetas, right? They both say E theta, but remember E theta and ER are actually traveling with the object, right? And so they're not actually pointed in the right directions. So if I come up here, if I look at what object A's, there's object A's ER, or car A, and this is E theta. And then object B, there's its ER, and there's its E theta. Right? So they're pointed in different directions. And that's what I was saying, I've been hinting along the way that like the polar coordinates is great for figuring out, like if I was saying what kind of forces do the occupants of this vehicle feel, polar coordinates nails it, right? You can absolutely, just from this, I have those accelerations, I equate those to forces, and I would feel what kind of forces they would be. That's kind of the next thing we're going to. But what it's not good at is telling you exactly what its position is, because they're actually in two different positions at this point, okay? And so you have to do a little something else. The easiest thing to do is convert it to Cartesian coordinates. Once everything's in Cartesian coordinates, that is a fixed reference frame, and then I can calculate the relative velocities based off of that. Okay? And then because it tells that angle being 25 degrees. And so what's really nice about this, B, it actually lines up with the Cartesian, right? Our x and y. ER is just in the x direction, E theta is in the y direction, so that one's not so bad. But then there's this guy who's kind of pointed off to the side. Right, you could just, right, I mean, you guys with it, if I gave you enough time, you'd be able to figure this thing out, right? I mean, it's just a little triangular stuff, right? If I put a little triangle there, right, I can figure out what the components of ER and E theta are. But also, I gave you those results once before. I gave you a little thing that said what those equations are. And I'm going to go up and copy it, actually. I'm going to cheat here. I gave you what those conversions are right here. Right? And so basically what you do, if you want, I mean, like I said, you could go back and you can figure out the triangles yourself, or you can just use these identities here. So basically every place that I see an E theta, I put in this, and every place I see an ER, I put this. Okay? And so let's do that. So let's convert everything to Cartesian really quick. Oh. 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 Like I said, car B is pretty easy because they already line up. But so we'll just do it for the A. So VA is equal to 36 in the E theta. And I just do the substitution with that theta over there. So this is just 36 times negative sine. The theta there is 25 in the I plus cosine 25 in the J. Okay, so I just literally just took that, and every place I see E theta, I go, boop, put it right there. Okay, and that does that conversion for you. And all it's doing is just breaking down that triangle and doing its x and y components. Okay, the velocity of B in Cartesian. That one's just going to be equal to 45 in the J. That one you don't really have. I mean, you could, if you wanted to, you could use that identity over there. Right, but I observed that, oh, look, that's the E theta right there for B. That's just in the Y direction. You could just do that. If you use the identity, you could. This doesn't break down. It would work. You just put it in the angle of 0 right there. You put it in the angle of 0, and it turns out to be all of it in the J. But yeah, this goes to, and then you're just left with that. Cosine 0 is 1, so you just end up in the J direction. Okay, so that's the velocity of A, velocity of B. Do the same thing for the acceleration. This one's a little more. Acceleration of A is just negative 36 squared over 1250 in the ER direction, which is equal to negative 36 squared over 1250 times cosine 25 in the I plus sine 25 in the J. I'm leaving these things all as kind of variables. You can actually carry out these. You could turn that into a number if you wanted to. I must have been lazy with my calculator that day, so I just left it in this form. Negative 45 over 1200 in the ER direction. Oh, that's just in the I direction. Everybody with me? Right. That's all of this is in the I direction because it lines up in that direction. And then now you go back up to that equation above. and just say, yep, velocity of B is equal to the, velocity of B is seen from A. B is seen from A is equal to the velocity of B minus the velocity of A. Now that it's in Cartesian coordinates, you could do that. Acceleration of B is seen from A is equal to acceleration of B minus the acceleration of A. Right. And I don't actually write those numbers down, just straight algebra there. And what you end up with, I'll put a dot, dot, dot. You can double check, you get these answers if you want. The magnitude of VB is seen from A is 19.6 feet per second. Next, the magnitude of acceleration of B is seen from A. You get 0.87 feet per second. All right, the key there is that it's got to be Cartesian coordinates in order to do these. They have to be in the same coordinates. They have to line up. Right? Do you have to do it as formally as this? Right, where I said, all right, I do it at polar coordinates, and then I convert it to Cartesian coordinates, and I do that. I mean, I myself like to do that because it's very procedural oriented and just like leads you right to like the right answer, right? Some people smarter than myself know that, oh, look, I'm looking at this, I'm gonna use my intuition. I know that like already I know that, you know, AB's this way and E theta's that way, and then really they know that like the acceleration, the centripetal acceleration is back towards the center like this, and they can break that thing into its components along the, like while they're on the fly and stuff, and they just do it all at once. That's fine. You could do it that way. Pretty soon though, real soon, we're gonna get to a point where if you try to rely like that, this your intuition can handle, right? But pretty soon we're gonna get into stuff where your intuition cannot handle it, right? And so having this very structured very structure-oriented approach to stuff is going to be money. We're going to need it. Yeah.
So when we find that last velocity, like the relative velocity,
yeah,
that doesn't matter at all the relative position, right? It's just the directions that they're moving.
If you calculate, so that's the magnitude. That's just the total magnitude. If you just carried this out, you would get a vector with an I and j component, and then it would be what it would look like. If you're at B looking at A, B is seen from A. So if you're at A looking at B, it would be how fast B looks like it's going relative to you, right? And so if there's nothing else out there, if there's no background or anything else, if you're like out in space and you looked at it, you wouldn't know which one was moving. Are you moving? Are they moving? But that's all you'd be able to say is what its velocity and its acceleration were relative to you. But once you add in the background and the ground and stuff, then you would know, like, oh, it actually isn't moving that fast. It's doing this stuff. It gets a little confusing. Are we good? I don't know if that was a bad explanation of it, but this is just the magnitude. Once I got the i's and j's, I did the square root of the sum of the squares, and that gives me these values right here. Okay. The next topic, right? I was so glad to get rid of. I don't like. I mean, it's okay. The kinematics is okay, but kinetics is where more interesting stuff happens. So if you had a chance to print out the next set of notes, we'll start kinetics here. Okay, so we're still in particles. We haven't got on to particles yet. So now everything else is just kinematics. It was all, right? We didn't say force. I mean, I would say force when I was lecturing, but not once did we write down forces and stuff, right? We want forces, right? As engineers, we need those. We need those forces because if we're designing the elements, right? If we're designing whatever it is we're designing, we need to know what kind of forces and stresses and things like that it's undergoing, because we need to design those. We need to make them big enough so that they don't fail, right? Another way to look at it is if I'm designing a rocket, I need to figure out what kind of force do I need to apply in order to get those accelerations, right? So we have to tie those things to each other, and that's what kinetics is all about. There's kind of three different methods we're going to do under kinetics. We're going to do force, mass, acceleration, FMA. We're also going to do work energy, right? And then we'll also do impulse momentum. Right? We'll cover each one of those things as we go along. But FMA, force mass acceleration, we just go to Newton's second law and do a free body diagram stuff. Work energy is my favorite, right? It seems like a trick that we use. And then we use impulse momentum for when we have collisions. Work energy kind of breaks down when we have collisions, but impulse momentum still works. Okay? And that seems somewhat magical as well. So we just did kinematics, right? Just a refresher, kinematics is just the geometry of motion. That's what we just finished. Kinetics is how do we tie forces back to accelerations, okay? What we do with this is we start out with Newton's second law. Right? And also I should say, I mentioned this before, one of the things that's nice about when we go into kinetics is it's very process oriented, right? I'm gonna lay out a process for you guys. If you follow the process, you're gonna get the right answer, right? You're gonna have a better time. If you don't follow the process and you start relying on your intuition, you're gonna have a terrible time. Okay, so although this first part you could probably rely on your intuition, but once we get into 2D rigid body stuff, it's gone. You don't have the skill set yet. You will someday. You just won't have it. Some of you will have it. I don't have it. And I'm a doctor. I have to bring that up every once in a while. I always joke that I want to be on an airplane or something. They're like, is there a doctor on the plane? He'll be like, it's me. And then oh shit, I'm not that kind of doctor. I always joke with that, but just last year, I was on a plane and somebody was like, is there a doctor? This guy was having trouble breathing. I was like, shit, probably not the best time to, it sounds funny to do it, but then when you're actually in that situation, you're like, yeah, nope, not gonna pull that one. That'd be bad. Not right. Okay. So that's it, right? Forces, sum of the forces, right, is equal to mass times acceleration. Okay. I saw at one time on an exam, someone wrote sum of the forces, like SOME of the forces, equal mass times acceleration. I was like, wrong sum. SUM of the forces equal mass times acceleration. That's Newton's second law. Okay. How we get these forces? These are going to come from the free body diagram. If you hate free body diagrams, I'm sorry. We're going to use them a lot still. Free body diagrams. And then once we get this acceleration equation, then the stuff we learned in kinematics come in. Right? So the reason we've been doing all that geometry of motion is because we still need it. We have to come back and actually do kinematics still. It's just we've stepped one step further back, and we have to come up with those equations for acceleration. And once we get those, then we do our kinematics. Okay, so that's kind of where we're headed. We're going to do this in 3 different coordinate systems, just like we did with kinetics or kinematics. 3. Which is Cartesian, normal tangent, and polar. I always kind of like to lay out where we're headed on each of these things. So that's exactly what we're doing. We're doing, starting out with Newton's second law. This is FMA. Sorry, we're starting out with FMA. And then we're going to do Cartesian coordinates with FMA. And then we're going to do normal tangent with FMA. And then we're going to do polar coordinates with FMA. All right. So in the Cartesian, is there anything else in there? Nope. So in Cartesian coordinates, what this looks like. Sum of the forces is equal to mass times acceleration. These are vector equations. I am writing them that way on purpose. What we do is we look at the sum of the forces in the x, in the I direction, plus, so this is just kind of expanding that vector of the forces. Sum of the forces in the y direction is going to be in the j direction, plus sum of the forces in the z in the k direction is equal to mass times acceleration in the I direction plus mass times acceleration in the y direction, the j, plus mass times acceleration z in the k. Oh, yep, okay. So you just take that vector equation and then just break it into ij's and k's, and that's it. Okay? And the way vector math works is all the i's are equal to each other. So some of the force in the x is equal to mass times acceleration in the x. Some of the forces in the y is equal to mass times acceleration in the y. And some of the force in z is mass times acceleration in the z. So you just break it into like three different problems, x's, y's, and z's. And what you end up with are these guys. Very easy derivation for this coordinate system. Look at the x, the y, and the z. Okay. So these are what we call these are the equations of motion. So those are called equations of motion. Like I said, this is very procedural oriented solution, so you can really follow step by step how to do these things. And so one of the things we're going to have to do when we get down to the solution procedure, the first thing we're going to have to do is a free body diagram. Okay, those are. You guys like free body diagrams or dislike free body diagrams? I'd like them. I think it's fun to draw. It's one thing I could do, right? It's pretty stupid. Draw a little picture, draw little arrows on it, right? They're going to be really key. They're absolutely key, especially when we move on into rigid body stuff. They're going to be essential. Okay, so I'm going to give you a procedure here for doing these things. And we're going to stick to them. Right, and and then also too, because they're so important. The reason, who do you take statics from? Who's statics from? Statics? What's that? The dean. I'm sure he mentioned free body diagrams. Is that guy? You guys are looking at me like you haven't heard of him before. Okay, I was like, if Ladine's doing it, I'm going to tell you this. If Ladine's doing statics without free body diagrams, I have to have a talk with Ladine. It's like, how the hell are you doing this? Okay, so they're so important that they're going to be worth points, right? So if you do it, you get points, right? That should give you if you do them correctly, you get points, right? So do them. Okay, and you need them to get to the right answer anyway. Okay, so I call this like a procedure, but really I'm going to call it a checklist. Oh, just think of it as a checklist. You don't necessarily, meaning that you don't necessarily have to do it in this exact same order. Okay, isolate particle or object. That's the easy one, right? Just isolate the part. In free body diagram or in particle dynamics, oftentimes it's just a point, a single point. You could draw your free body diagrams about, or you could draw the actual object if you want. Okay, but everything's concentrated in one location, right? We're gonna replace supports with appropriate forces. Okay, or moments. Depending, we have rigid body stuff, there'll be some moments. Sketch, applied, loads, or forces, right? Either way you want to look at it, same thing. For pick coordinate system and label diagram. Because we're going to have, like I said, we got 3 different coordinate systems we're going to deal with. 3 different coordinate systems, so then you want to put it on there. And then clearly label it, right? Show where your x's are, show where your y's are, show where your ERs are, your E thetas, right? Whatever coordinate we're at. And then label dimensions, angles, /angles, etc. on drawing. Right? If you have a nice, clean, tight free body diagram, it makes some of these future steps way easier. Okay? Just really nice and clear, laid out nicely. Okay? I'm going to stick to this plan. Okay? The solution procedure we're going to do. So that's the checklist just for free body diagrams. We'll do some examples here in a minute and put all this stuff to work here. And so the solution procedure we're going to do is the first thing we're going to do is a free body diagram. Second thing, I'm going to write EOMs. Right, those are the equations of motion. I guess I'll write that. Right, we laid them out. Sum of the force in the x is equal to mass times acceleration in the x. Sum of the force in the y, mass acceleration y. Sum of the force in the z, mass times acceleration in the z. 3. We're going to do kinematics as required. And sometimes you need them. Sometimes you need kinematics. Sometimes you don't. And then solve. Right. And so we're going into every one of these problems is exactly that way. Right? So if you open it up, you open up your homework, and you're like, oh my God, where do I even start? I don't even know what to do. Do this. Okay, literally just do this, right? Like, I know it's gonna be confusing. Some of these are just like, oh my God, there's all this stuff going on. Things are moving, what do I do, right? Do this. Let's go back to this.